Alright, these are the problems from page 327, and this is using the new theorem. I didn't make a big deal of it in the notes that I sent to you over Edline, but this is the fundamental theorem of calculus, and it is how you evaluate a definite integral without finding area geometrically or without using your calculator. It gives you the calculus and algebra way of evaluating a definite integral. So let me just review what the theorem says. If you're going to find the definite integral of a function from a to b, what you're first going to do, the first step, is you're simply going to ignore the bounds of the a and the b, and you're going to focus on this as if it were an indefinite integral, and you're simply going to find the antiderivative of f of x. And when you find the antiderivative of f of x, you will get capital F. In other words, that's just denoting the original function and giving it a different name. Little f is the derivative and big F is the original function. So you find the antiderivative and you evaluate it at b, upper bound always, minus f of a, lower bound. So it's always upper bound, if you didn't pick up on that, minus lower bound, of course, evaluated, not just simply those two numbers. And that's how you evaluate a definite integral using calculus and algebra. And it's a very, very simple process, and that's how we're going to do these problems. There was something, again, the plus c, I just want to re-emphasize, you'll notice that when I find the antiderivative, I am not going to put in a plus c. And the reason that we're not putting in a plus c is if we're taking the function and plugging in an upper bound, and then taking the same function and plugging in a lower bound, since we're subtracting, that plus c would subtract out anyway, and it becomes irrelevant for a definite integral. It's still important for an indefinite integral, okay? So let me get rid of that, and let's start some, and I'm only going to select a few problems because they all follow the same pattern, and I think you'll be able to handle this. Alright, so let's look at problem number 5. Just start with a simple one. From 0 to 1 of 2x dx. So step 1, find the antiderivative of the function. So the antiderivative of 2x would be 2x squared over 2. Now notice what I do here. I've now put it in brackets, and I'm going to evaluate it from 0 to 1. So follow the pattern of how I write my answers and how I do my work. Simplifying that, of course, would just give me x squared evaluated from 0 to 1. So it's going to be upper bound in place of x. So I get 1 squared, which is 1, minus lower bound in place of x. 0 squared is 0, and 1 minus 0 is 1. So if we were to graph that function and we were to look at it as area, we would get an area of 1. Notice number 6 doesn't have an x. Well, that's no big deal for us because we know how to find the antiderivative of 3. And this is dv, so make sure you use the right variable. When you find the antiderivative of 3, you get 3v evaluated from 2 to 7. And so that would be 3 times 7 minus 3 times 2, which would be 21, minus 6, which would be 15. Let's jump over to number 10 because 7, 8, and 9 would be done basically the same way. In number 10, we just have 3 terms, so we're going to go from 1 to 3 of 3x squared. So I'll have 3x squared plus 5x minus 4 dx. We're going to integrate or find the antiderivative of each term, so we get 3x cubed over 3 plus 5x squared over 2 minus 4x evaluated from 1 to 3. And of course these 3's will subtract out. And then I'm going to substitute 3 in place of x, and 3 in place of x, and 3 in place of x, and do the arithmetic. So that would be 3 cubed is 27, divided by 3 is 9. 3 squared is 9, times 5 is 45 over 2. And yes, you will encounter fractions, do not be afraid. Minus 4 times 3 is 12. So that's 3 plugged in, and now I'm going to subtract. I'm going to substitute 1. So 1 cubed is 1. You know what? I messed up the last one because I had already divided these 3's out. I just realized that now. So 3 cubed is 27. Okay, so in the other one, 1 cubed is 1. And then I'll have plus 5 halves minus 4. Now the easy way to do this is if you can start with your fractions. 45 minus 5 halves would give me 40 halves. And then look, the fractions will disappear and I don't have to worry about getting a common denominator, at least in this problem. Then I would take the negative 12 minus 1, which is negative 13, plus 4. Negative 13 plus 4 would be minus 9. So I have 40 divided by 2, which is 20 minus 9, which is 11. So it's really not that bad. Believe me, you're probably going to find the arithmetic the most challenging part of this entire process. Let's get rid of that, and let's pick some others to work with. Number 11, the way you're going to handle that is before you start working on it, you're going to have to square the binomial and rewrite it as 0 to 1 of 4t squared minus 4t plus 1. That's the only big deal with that. Square it out. Square the whole thing. A binomial times a binomial gives you a trinomial. Number 12, that one follows the pattern that we've been doing in the other one. Number 13 has something a little bit different. You have to sprinkle the algebra. You have to rewrite it thusly to be 3x to the negative 2 minus 1 dx. Then you're going to find the antiderivative. So that would be increase the power by 1. Now be careful with negatives. Increase the power by 1 and divide by the power. So that would be negative minus x from 1 to 2. Now what you might want to do, since this has a negative power, is go ahead and move it back down and then evaluate it. So that would be negative 3 halves minus 2. That's when I plugged in the 2 minus negative 3 over 1 would be negative 3 minus 1, and this would be negative 3 halves. This would be 4 halves. So that would be negative 7 halves if I'm doing my arithmetic correctly, because 4 halves is 2. Minus negative 3 minus 1 would be negative 4. So that would be negative 7 halves minus negative 8 halves. So that would give me a total of 1 half. Now I am doing these fast and I could make an arithmetic error. You do have the solution manual, so you can check behind me to make sure I did that correctly. But you can handle the fractions. The main thing is the rewriting and being careful in the integration. Number 14 involves the same thing. You're going to do an algebra rewrite by moving the u squared to the numerator and making u to the negative 2. Number 15 has something a little different. Not much different. It's a classic problem that we've seen over and over again. Notice the first thing I'm going to do is change the square root of u into u to the 1/2 power. And then I'm going to do a rewrite, not finding the antiderivative yet. That would give me u. This is to the 2 halves. Minus 1/2 would be u to the 1/2 minus 2u to the negative 1/2. Notice every term gets that u to the 1/2 in the denominator. Then I can find the antiderivative, so that would be u to the 3 halves divided by 3 halves, which is times 2/3, minus 2 to the 1/2 divided by 1/2, which is times 2, from 1 to 4, so that would be 2u to the 3 halves over 2 minus, I dropped a u. I knew something was wrong there. Minus 4u to the 1/2 power. Now, you can do this without a calculator. I'm going to substitute in the 4. The square root of 4 is 2. 2 cubed is 8. Or these two right here are going to divide out. So let's do that again. The square root of 4 is 2. 2 cubed is 8. Still substituting in the 4. The square root of 4 is 2 times 4 is 8. Alright, so that makes it easy. Again, I'm assuming my arithmetic is good. I'm going pretty fast here. Let me check again. Square root of 4 is 2. Cubed is 8. Square root of 4 is 2. Yep, looks good. And the next one, 1 raised to any power is 1. And in the next one, 1 raised to the 1/2 is 1 times 4. So I get 0 minus negative 3, which is 3. All right, let's take a look at, so that takes care of 15. In number 16, just be careful when you increase the power, you're going to add 3/3. That's adding 1. So you would get 4/3, and you would multiply by 3/4, the reciprocal. Let's go to number 18. Just working as many of these as I can. In problem number 18, I'm going to do a rewrite first, and that's the key to most of these problems. Oops, 1 to 8 of 2 over x to the 1/2 power dx. Now notice that everything is square rooted. So another way to write this, and this might be the easier way for you to write it, is to write it as 1 to 8. Keep the 2 under the square root because we're not going to integrate that. That's just going to be a coefficient. X to the negative 1/2 power. We're going to bring that x to the numerator, and we have to change its sign. So then when I integrate, I'm going to actually pull the square root of 2 out front. Remember the properties that we just focused on. So when I find the antiderivative of that, I will get square root of 2 times x to the 1/2 power divided by 1/2 is the same thing as times 2, evaluated from 1 to 8. So that would give me square root of 2 multiplied by 2 square root of 8 minus 2 square root of 1, which is 1. So in other words, I plugged in the 8 and I plugged in the 1. This is the square root of 2 that was from the outside. Simplifying my radical on the inside, that would be 2. Simplifying this radical, I will get 4 square root of 2 minus 2. Distributing, I will get 8 because the square root of 2 times the square root of 2 is plane 2, and plane 2 times 4 is 8, minus 2 root 2. Again, you know what? It's going to give you the most trouble is just simply dealing with this arithmetic and radicals and fractions and all that stuff. But that's why it's important to do all of the practice. All right, let's keep moving on. Do a few more of these. Number 19, that's a little fraction work. All I'm going to do is rewrite it. I'm not going to take it any further. When you rewrite that from 0 to 1, you would have, actually, I would pull the 1/3 all the way out front by itself. It'll make your life easy. X minus x to the 1/2 dx. And I think you can see by pulling that 1/3 out, you don't have to deal with it with each term, and it makes the problem a lot easier. Number 20, what I'm going to do there is I'm going to, that was 19, and number 20, I'm going to distribute that square root of t that's in the back. So that would give me 0 to 2 of 2 square root t, or t to the 1/2 really is how I would rewrite it, minus, now this is t to the 2 halves, multiplied by t to the 1/2, that would give me t to the 3 halves. That's just good old-fashioned algebra using powers. So the key to number 20 is doing a rewrite. Now in the next step of 20, you cannot take this 2 off of this t to the 1/2 unless you make 2 separate integrals. In other words, in number 19, the 1/3 belonged to both terms. Both of them were being divided by 3. So be careful with that property. You can pull it out if you were to separate this into 2 different integrals, which is legal from another one of our properties. 22 looks like a fun one, so let's take a look at that one. 22, let's see if I can rewrite that as I'm going along. Everybody is divided by, well, first thing I'm going to do is get that 2 out of there, move it out in the front as a 1/2. So now it's out of the way. And this cube root of x is x to the 1/3, so I'm going to deliver it to everybody in the numerator. So I have x here to the 3/3, take away 1/3 would be x to the 2/3. Minus, this would be 2 is 6/3, take away 1/3 is 5/3, so that would be x to the 5/3. I'll take it one more step to find the antiderivative. Now notice they're very friendly to you here. They're giving you perfect cubes. See, we're going to be dealing with perfect cubes here, and they're giving you a -8 and a -1, which are perfect cubes. So I'd have 1/2 of, increase the power by 1, that would be x to the 5/3 multiplied by 3/5 minus x to the, I'm adding 3/3, that would be 8/3 times 3/8 from -8 to -1. And then I'll take it one more step. That would be 1/2 of, I'm going to substitute in the -1. Cube root of -1 is -1 to the 5th would be -1, so that would be -3/5 minus the cube root of -1 is -1 to the 8th is +1, so that would give me 3/8 minus, here comes the lower bound, the cube root of -8 is -2 to the 5th. -2 to the 5th is -32. -32 times 3 is -96/5. And then the cube root of -8 here is -2. -2 to the 8th is positive, is positive 256, and 256 times 3 is 768/8, which is probably reducible. That one was not loads of fun, but could do it if I had to without a calculator. And so from there, you're going to clean up and do the arithmetic. Now, 23 and 24, I definitely want to look at. And I'll look at 25, but mostly I'm going to warn you that I would really look at 23 and 24. Now, your book gives you an example of how to do this, but I want to show you how I recommend dealing with most of your absolute value problems. Now, notice the difference between 23. This is just linear, 2x minus 3. It's a little different when you start dealing with the quadratic, although it still can be done. And 26 is a quadratic, and it offers a little bit more of a challenge. So let's start. 24 again is linear. Let's start with 23. When I am trying to find the antiderivative or the integral, definite integral of an absolute value function, my recommendation is to graph it. Now the key is finding the vertex. So you're going to take the numerator and set it equal to 0. What makes 2x minus 3, and this would probably be done in your head, equal to 0, and that would give you x equal to 3/2. So the vertex of the absolute value is 1, 2, 3. So 3/2 right here, 1 1/2. Now, that's not the perfect graph. I only plotted the vertex and then I just graphed the function. What I need to know is what is the value of when x is 0? So if I plug 0 in here, I get -3. And the absolute value of -3 is +3. Okay, so that's important because all I'm going to do here is I'm going to go back to the good old-fashioned way of integrating by finding area. Now I'm going to do the same thing with 3. 1, 2, 3. I'm going to substitute 3 in place of this. 3 times 2 is 6, and 6 minus 3 is 3, and the absolute value of 3 is 3. So you'll notice I have two triangles. This is 3 by 3 halves. So we have 1 half of 3 times 3 halves. So that gives me 1 half of 9 halves, which is, when I multiply, 9/4. Now we know that this has the same amount of area, don't we? This was 1.5. This is going to be 1.5. So this one has the same amount of area. So we have 9/4 for this area and 9/4 for this area. So we have a total of 18/4 as the area, or reduced, of course, is 9 halves. Okay, so again, I would recommend graphing them. Now, if you take a look at the book, it will show you what it shows you in the book is it says to integrate from the lower bound of 0 to the vertex, and this would be the negative side of the absolute value. Now, what do I mean by negative? The slope on this side is negative. And then add it to the area from the vertex 3 halves to the upper bound of 3 of the, quote, positive side of the absolute value. Notice I've dropped the absolute values. Now you can do the problem that way. It involves doing two different problems, but these are two strategies to deal with it. I tend to recommend the graphing method. Let's take a look at number 24. I'm going to get rid of that, so if you need to look at this problem more, you can stop the video and just kind of stare at it and look at it and replay it or whatever. 24 just bumps it up just a little bit. In number 24, we're going to, now notice the first thing I'm going to do is I'm going to pull the absolute value away from the 3. So I'm going to use a property and rewrite it this way. Now integrating this side is very easy. I'm going to integrate 3 to get 3x, and I'm going to evaluate it from 2 to 5, so I get 15 minus 6, which is 9. So I'm just going to hang on to that because I'm going to have to subtract whatever I get for the absolute value. Now again, what I would do here is I would graph this, and this would be 4 to the right, 2, 3, 4. So my vertex is at 4. I want to know the value at 2. So 2 minus 4 is negative 2, and the absolute value of negative 2 is positive 2. So this is 2, 2. So I know this is 2 by 2. 2 times 2 is 4. Half of 4 is 2. So the area of this triangle is 2. I'm going to do the same thing with 5. 5 minus 4 is 1, and the absolute value of 1 is 1. So 4, 5. So this is a 1 by 1, and so the area is 1/2. I wrote a 1, but it's 1/2 base times height. So the total area would be 2 plus 1/2, which would be 4 halves plus 1/2. So it's going to be minus 5 halves, minus 5 halves, minus 5 halves. So it would be 18 halves minus 5 halves, which would be 13 halves. I just want to look back and make sure I did that right. Absolute 5 minus 4 is 1. Absolute value of 1 is 1. So it is a 1 by 1, and half of 1 times 1 is 1/2. Okay, so that's how I would handle that problem. Again, for the absolute value part, you could, if you wanted to, have broken it up to go from 2 to 4 of the negative side of x minus 4, so to speak, plus 4 to 5 of the positive side of the absolute value, which it just gives you more algebra and more arithmetic to do. But you really, really, really need to study these strategies and this technique. Again, I'm going to get rid of this because I want to look at number 25. Now, 25 is not undoable, but it is a little bit more challenging because it's x squared minus 4. So think about the graph of x squared minus 4. Normal graph of x squared minus 4 would be a parabola translated down 4 units. And when we take the absolute value of that, the graph would, this piece, all this area down here would flip up. So the x-intercepts are at positive 2 and negative 2. So the graph would look like, I'm kind of cheating a little bit here, like this. Okay? And so in this case, I probably would break it into, I think what I would do is I would go from, where's this going from? Oh, it's only going from 0 to 3. So we're only focusing on this part. So if I were going from 0 to 3, I would do the opposite of 0 to 3 of x squared minus 4. Now the reason I'm doing opposite of, remember that area was negative, but now I want to pick it up as positive. And then I'm going to go from, oh, I'm sorry, that would be 0 to 2, stopping right there. And then I'm going to pick up 2 to 3 of x squared minus 4. These are a little bit more challenging because graphing it is not necessarily going to cut it because I can't do the geometry like I could when it was linear. And we'll talk more about that in class, but I just want to give you a preview. Okay, getting tired here. Let's take a look at just a few of the trig ones, and then I'm going to stop, and you can come in and see me at lunch or ask me more questions in class. Let's do number 28 because 28 has a trick in it. In number 28, this is one of our good old Pythagoreans from pre-cal, and you know as well as I do that 1 minus sine squared is the same thing as cosine squared. And so we have cosine squared over cosine squared, which is really 1. And when we integrate 1 in terms of theta, we get theta evaluated from 0 to pi over 4, which is, oh, come on, which is pi over 4 minus 0, which is pi over 4. So that was just a little pre-cal trick there. Let's do number 33. Let's do number 30. Let's 33 and 34. Actually, and also take out, that's 23. Take out 25. No, it's not. It's 35. Take out 35 and 36. I didn't mean to assign those to you if I did. So let's do number 33. Number 33, I'm going to pull the 4 out front and make what I need to see a little bit more recognizable. And I have secant theta, tangent theta, d theta. And this is where I'm going to ask myself, who has a derivative of secant theta, tangent theta? And that would be secant theta from negative pi over 3 to positive pi over 3. Now, it's going to be probably easier if you think of that as 4 times 1 over cosine of theta from negative pi over 3 to pi over 3. That's going to be 4 times 1 over, so the cosine of pi over 3, pi over 3 is 60 degrees, and the cosine of 60 degrees is 1/2. So cosine of 1/2 minus negative pi over 3 is in the 4th quadrant, and cosines are still positive there. So I'll still get 1 over 1/2. So that's going to be 0, and 4 times 0 is 0. Hopefully I didn't make any arithmetic errors, and think we're okay. Let me know in class if I made any errors. It's okay. I'm running out of energy here. Let's see if I spy anything else kind of interesting. 32, got to do an algebra rewrite and make it 1 over 5. X divided by x is 1 plus 1 over x. Make sure that you give that x in the denominator, everybody. And when you integrate, find the antiderivative of 1 is x, and the antiderivative of 1 over x is ln of the absolute value of x from 1 to 5. And then you're going to get 5 plus ln of 5 minus 1 plus the ln of 1. Now the reason I'm not putting absolute values around those numbers is because the absolute value of 5 is 5 and the absolute value of 1 is 1. So now I have 5, oh by the way, ln of 1, e to what power is 1? That's just a 0. So 5 minus 1 is 4 plus ln of 5. I think I'm going to stop there, and if you have other questions I will be glad to answer them in class, but I wanted to get these videos online, so if you wanted to look ahead and be thinking ahead, you could do that.